So now we're almost finished at looking at the case where we have a linear system with an infinite number of solutions. So let's look at where we are now. We had to prove the things that we wanted to prove were first we wanted to determine when that was going to occur, and we just proved that in the last video. That was result one. We showed that we have an infinite number of solutions when the number of linearly independent rows is less than a number of columns. And now we want to show how those solutions are related to the kernel of A. So I'm going to show that there's a relationship between the basis vectors in the kernel of A and the way in which the solutions can be expressed. And the last thing I want to do is I want to show that this form of the solution, which generally has a parametric form, is actually such that the number of parameters in the solution is actually equal to the number of basis vectors in the kernel. So this in a sense tells us the dimension of the solution set for any one B. Okay, so let's take a look and see how we're going to prove results 2 and 3. Okay, so for result 2, what we want to show is that every solution to AX equal to B can be written in the following form. It can be written as any solution to the system, which I'm going to call XP for the particular solution, and another vector which is in the kernel of A. Notice this looks a great deal like how we write the solution to a non-homogeneous linear ordinary differential equation. You might remember we write it as a particular solution, which is any solution, plus a homogeneous solution, and that's the solution to the homogeneous equation. Well, what are vectors in the kernel of A? Those are solutions of the homogeneous system, right? Okay, let's go ahead and prove this. So let's suppose that we have any solution to AX equal to B, and let's suppose I have another solution. I know I have an infinite number, so I can suppose there's another solution. And I notice that their difference is in the kernel of A. A times their difference is the zero vector. Okay. So therefore it automatically follows, just by solving for x, that x is written as any solution of AX equal to B plus some vector that's in the kernel. And that proves the second result. Okay, now we have to prove the third result, which is that when we write the solution in parametric form, the number of parameters is equal to the number of basis vectors in the kernel of A. And I want to do this with an example just to kind of show you, because we haven't worked much with the parametric form for cases where we have an infinite number of solutions. So let's just take an example. So I'm going to suppose that I have this linear system, okay? And let's go ahead and use Gaussian elimination. You can stop the video if you want, but I'm going to go ahead and write out the row echelon form. When you get done doing Gaussian elimination, you'll get a row echelon form like this. And I'm going to notice that when I write out those systems of equations, the first two equations are going to give me the following, okay? And that then lets me write the general solution like this. U is written like this, V is equal to V, W is written like this, and Y is equal to Y. And you notice I can tweeze those apart, right? I can put all the vectors that have V together, all the vectors that have a multiple of Y together, and then this vector here together. And these three will add up to this. So I'm kind of decomposing the solution, right? Notice I've written the general solution as a parametric form, right? In other words, V and Y are my parameters. So this is the parametric form of the general solution for this non-homogeneous equation. Okay, what I want to show now is I want to show that the parametric part has to be in the kernel of A. And here's how I'm going to do it. I'm going to look at the solution. This is the form of the general solution. And I'm going to notice that these are that this is a solution for every possible value of v and y. So let's let v and y be equal to 0. So x sub 0, 0 is a solution. But when I let y equal to 0 and v be any real number that's not 0, this is also a solution too. Now I know that the difference of any two solutions has to be in the kernel of A. That's what we just showed. Okay, so this minus this has to be in the kernel of A. And of course this is one of the vectors that's being multiplied by a parameter. So this vector has to be in the kernel of A. So I've shown that this vector is in the kernel of A, and I can do the same sort of thing to show that this vector is in the kernel of A. Again, let y, v both be equal to 0, and now let, actually I want v equal to 0 here, sorry. Okay. And again, their difference has to be in the kernel of A. So I've shown that both of these have to be in the kernel of A. So notice that this is all possible linear combinations of two vectors in the kernel of A. All right. And it turns out that the kernel of A happens to be spanned by this space. How do I know that? Well, I can actually solve the homogeneous system, and I'll show that this is all the possible systems. So this is like my particular solution, and this is my homogeneous solution. I claim that if I let b be equal to 0, this will be my solution. Okay? So I haven't really proven it, but hopefully I kind of convince you, or at least illustrate what's going on. Before we end, I want to show you a little bit about the geometry of the solution set. So let's consider what the graph of y equal mx plus b is. Well, notice if we take the homogeneous linear system, y minus mx is equal to 0, that's a line going through the origin, and then I shift it by b, and I get the final solution, okay, to this non-homogeneous linear system. So let's ramp it up a little bit and look at the more general case. The more general case says that the kernel, just like this was in the kernel of this linear system, it says that the kernel is basically, and I shouldn't really say a plane, it's really a subspace, but it's a subspace that contains the origin. Okay. Instead of a line now, we have a subspace. And what happens is I'm going to add the particular solution to it. And it's going to translate the solution just like B translated this line. Okay. And now this black plane is the shifted kernel. And so this tells us that the final solution is a translated, and I really shouldn't say plane, I should say subspace. I'm going to change that in the notes. So the idea is that the final solution is basically the kernel of A that's been translated by any solution of the linear system. That kind of gives you a little bit of insight as to what the geometry is like. Okay, we're going to go on to the case of zero solutions because that's going to let us talk about linear regression a lot in the next video.